Let me know once my screen is up. Is my screen visible now?
Yes.
Okay, fine. So I'll just explain in short related to, for example, if those who are not attended the yesterday's lecture, it was complete an overview about what is actually synthesis. Okay, so the synthesis is just a conversion of a high level language. Okay, a high level language is nothing, just your Verilog code, which is being written in either Verilog, ideal code which is being written in either Verilog or a VHDL. Okay, the way it is being written, it does not have any technology related notion. All the format which is being mentioned is just your, it's technology independent. Okay, and the process of synthesis involves like converting your this high description language, which is nothing but your RTL, to a gate level netlist, because silicon understands the languages of gates. Okay, so we understood what are the steps that are being involved in the synthesis. Okay, in short, synthesis is called nothing but your TOM model, right? Which is translation, optimization, and mapping. Okay, so we understood that in translation, what we do is we just convert an RTL code into Boolean logic. Okay, and it is still not yet optimized. What happens in the optimization steps? It does a lot of optimization based on whatever your constraints that you have been provided. It tries to rectify it or reduce it, for example, either using K-map or your Queen-McPherson method or your boundary optimizations. It uses various techniques and try to optimize it, okay, so that you meet your PPA targets. PPA is nothing but your power, your performance, and your area. And the third and the final step that is being involved in synthesis is mapping. Till now, the RTL person doesn't is not having a notion of what is the kind of tech node that you're going to use, right? Whether you're going to use TSMC 5 nanometer or you're going to use Intel 18A node, doesn't have that notion. It's just a pure independent technology code. So now you have to map it, right? So this mapping is done using your whatever the libraries you have, right? From that library, the normal AND gate is mapped to a technology dependent gate. Okay. Then we looked at what were the different kind of inputs, like what is an RTL, what does RTL stands for, register transfer logic, synopsis design constraints. There are different kind of libraries, which is logical libraries and the physical libraries. If you are doing a power aware synthesis, in case you can provide a UPF. If you are doing a physical aware synthesis, then you can provide a DEF. Okay. And then we looked at the primary output of this was related to a netlist, which have a gate level descriptions. And then the reports and the logs. Okay. So today, what we are going to study is in detail description about what are the input files that we are going to provide for your synthesis. Okay. So when you say about input files, right? So what the primary input file which we discussed yesterday for synthesis is, can anybody answer just very quick? What's the primary input file? Just are also the important files, but what's the primary input file that is being provided in synthesis?
RTL file.
.v file.
Yeah. So RTL is the file, and that has an extension. Normally, the someone answered it as .v file, right? Because it is either used for extension stating that it is a Verilog or a VHDL file, correct? So we took an example yesterday. I showcased you an example of, I think, a full adder, correct? Where I depicted you how does an RTL of a full adder look like, and how does a, once it is being synthesized, how does a gate level netlist of this looks like. Along with that, we discussed about different libraries. Okay. So the first library file that we are going to discuss is called as timing library. In general, it is referred as timing library, but you can call it as logical library. Okay. The bigger way to, for example, if I want to say that the, for example, the library has to be classified, the library is classified into two things. One is your logical library. Okay. And logical library itself is called as your timing library, and other thing is which is physical library. Okay. So now, as the name suggests, if a library is logical, it just states what are the logical information about that cell. Okay, whether what the functionality is does, what is its timing related information. Okay, what is its power related information. So these different parameters. Okay, these different parameters, or you can call as attributes or the specification about the cell, Okay, standard cells. Okay, see, you guys know, right? The standard cells can be classified into broadly two classes. Can anybody answer it? Guys, yeah.
Combinational cells and flip-flops. I mean,
Okay,
standard,
yeah,
I mean,
yeah.
sequential and combination.
One is combinational cells and one is your sequential cells. Okay, they all come in your category of standard cells. Combinational cells have nothing to do with the clock, while all the sequential cells you say about your latches, your flip-flops, your synchronizers, okay, all these cells, even if your memories, it has a clock related to it. So these all comes in a kind of a sequential cells. Okay, so all the standard cells related different attributes, whether it's related to timing, power, area, is present in your logical library. Okay, then in detail we will discuss about what is the physical library. Okay, as the name suggests, physical attributes, right? How does it looks? What is its size? And what metal layer it has been built? Correct. So that all information will be present in your physical library. Okay. Now let's continuing about what is actually a timing library. So the extension which I have
Ma'am,
mentioned.
I have a doubt.
Hmm?
Physical only cells is comes under standard cells or other?
See, it comes under a category of standard cells, but within standard cells, it is a kind of you refer it as a physical only cells. Whether you have it called as tap cells, you call it as boundary cells. Okay, you can call a spare cells is normally people term it as spare cells as a physical only cells, but physical only, what is physical only cell, right? If you tell me, physical only cell is something which doesn't have any input or output. Okay, if you ever look
Okay.
into the design of any physical cell, physical only cells, it will never have any input or output. It will only have power and ground related pins. Okay, that's why they are termed as physical only cells. Okay, but it will come in the category of standard cells itself.
It is a one type of standard cell.
Yeah,
Physical only.
yeah. See,
Okay, okay. Thank
every
you.
all the cells is clubbed up into your bucket of standard cells. Okay, but
Okay.
in within the VLSI, we have, for example, if we are using some cells, for our understanding, we term some cells as physical only cells. Some cells, when you're doing at your floor planning, you will tell some cells as you will call some cells as macros, or you will call it as IPs. IPs are nothing, you call it as intellectual properties, other hard IPs, soft IPs. Some cells you give it as a bifurcation called as pre-placed cells, right? They're also all the cells belonging into the bigger bucket, which you call it as standard cells.
Ma'am, what is the difference between macro and IPs?
Macros and IPs are nothing but the two different terminologies being used for the same things. IP is nothing. For example, if you are designing, if you go in detailed description, hard IP is equivalent to macro, two different terminologies for the same thing. Now, what happens is within this, you have two different bifurcation. One is you call it as soft IPs, one is you call it as hard IPs. Okay, now let's take an example of for hard IPs. Let's say, see, when an industry designs a big complex logic, okay, whether you're calling it as, for example, if the MediaTek or Qualcomm is building any chip related to mobile phones, okay, they are building a Snapdragon processor for, let's say, 13 gen, okay. So these are all the complex designs. Now what happens is they are not going to build all the standard cells. Okay, so what they do is they buy it from a foundry. Okay, now similar what happens is instead of the standard cells, there are something which are complex logic. For example, let's say memory. Okay, so Qualcomm has an option, either they can inbuild their own memory, or one thing is that they can go in the market and buy it from the company that are very good in developing these memories. Let's say memories are being built by the great memories built by, let's say, Micron, or let's say by Sky Hynix. Even the Samsung has a great development in the memory side. Okay, so what they do is they go and say them, I need your memory, just give it to me. So what happens is, right, when they give you it as in form of IPs, internally you cannot look at the structure like how they have designed it because it's their patent. Okay, you cannot copy it or you cannot look inside what is the code. The only accessibility that you will have is their pins. Okay, so what happens is hard macros can never be altered. You will get it in the form of a B box where you are only allowed to access what are the pins? Pins are in which layer? Okay. Then there is something which is called as soft IPs. What happens is, for example, many industries, like there are different kind of structures they built on their own. It's not it is a combination of different cells they put upon. Let's say level shifters, right? In the lecture where I gave you about what are the different kinds of low power cells. Okay. So what they do is, instead of buying it, they know that, okay, I can build this cell on my own. I will use some technology, I will use a flow and develop this. So what happens is they just get a very synthesizable form of a code. Okay, so now they are accessible to the code, right? You can look at it, how they have been designed. You can optimize it as per your requirement. So it's not a black box. It's like it's visible and you can optimize it and generate an IP according to you. So that's soft IP. Okay. So IPs and macros are equivalent. There is no difference between macros and IP.
Okay, ma'am. Okay, got it.
Okay. Then let's proceeding ahead. So, okay. So for example, .lib, right? As I stated. See, this .lib is an extension for this library. Doesn't mean that I have just taken it in the form from lib and it is like library. Okay, there is something which is called as format structures. Okay, this .lib stands for liberty format. Okay, if anybody asks you what is .lib, why does it then timing lib have it in format of .lib, right? Timing library, physical library is in the form of left, right? It's not in the form of lib. Okay, so lib, when you said, it is a kind of it's not an it's an extension which is a format defined by the industry standard, and it is called as .liberty format. Okay, now the way in which this file is written, okay, there are different ways. See, if you are a person, let's say there are four folks in working. Now one person is from Maharashtra, one person is from Karnataka, one person is from Punjab. Okay, and they only know their regional language. Correct. Now the person from Maharashtra will only know Marathi. The person from Punjab only knows Punjabi, while the person from Karnataka only knows Kannada. Okay. Now the same way, if for example, if I have to tell the tool into a language, tool doesn't understand English, Hindi, Marathi. Okay, it understands in only specified formats or files. Okay. So the way in this timing libraries file is being defined is called as SKI format. Okay, because there is format for SKI, there is a binary format. Okay, so this is in the format of SKI with an extension of .lib. Now you have to understand this file. From where do we get this file? Okay, now you understood. For example, I gave yesterday, I was giving you the example, like we are preparing we are a chef, okay, and we are preparing some recipe related to anything. Let's say today we are preparing momos. Okay, so now I told you that you are building anything, so you have to take some masala. Either it can be from your Catch brand, or it can be from Everest or from MDH. Okay, so these are the companies which build the masalas. You can just go to the shop and buy it. Okay, go in the pantry and take it up. So similar way, these standard cells are being designed by various organizations. It can be either from TSMC, or if you're using it from Synopsys, you can say Synopsys. If you're using from Intel or from Samsung. Okay, so the company which provides you this is, you call them as a library vendor. Okay, they are selling their library. So they are called a standard cell library vendor, or you can call, if you're getting it from foundry like TSMC, GF, Global Foundries. Okay, so this file, you get it from the standard cell library vendor, or you get it from the foundry. Okay. So a very brief overview which you understand that this
Ma'am, what
library.
about .db file is one of the timing library. Uh, we are
Okay.
using.
So so see what happens is, if you have ever opened lib and .db, you'll understand the meaning is, when the tool has to process it, right? It does an internal, there is a way that the tool internally does this lib to db conversion. Okay, so that this format is understandable by the tool in the faster way. But way, if we have to read it, right, because we have to know what's the logical information present in it, we can't read the .db format, correct? So we have to take it as an input in .lib, We provide it to the tool. Tool internally does a lib to DB conversion. But we can't read the .db file. We are only, the SKY format is readable. Okay, .db, it's like you have converted into binary. You can never read a binary file. Okay, you can only read an SKY kind of a file. Okay, so yeah,
Okay,
so we just,
only we give .db file. So then tool will do the conversion.
see, if you're already giving it a .db file, then what's the use of tool doing it, right? Tool will do it for you, correct? If you already have .db file, pass it in the form of .db file. But this lib to DB conversion is also done by some compiler, correct?
Yes, ma'am. Yes.
The vendors doesn't provide you in the form of .db, correct? If you to go it from, either you go and buy your library from TSMC or Synopsys, you will always have a .lib.gz format, okay? Gunzip means they have zipped this file, there is nothing different. You'll have it, but you are the process, you tell the tool or compiler. Guys, please don't try to access the screen, okay? Fine. So the tool, the compiler has to do this conversion for you. Okay. You don't get the .db file directly from this vendors. Okay, guys, I would just state that let's keep all the doubts at the end because it restricts my flow, right? And once you note down all your queries, I'll address it at the end once we have completed this lecture because it's kind of a hurdle in my lecture. Okay, is that fine?
Yes, ma'am. Yes. Okay.
Okay, sure. So where were we? Okay. So you understood, right? That uh, this library, the logical library, or in general you can call it as timing library, has an extension of .lib, which stands for liberty. It is in the format of SKY. The person who asked the query that this lib to DB has to be done by the tool, but the vendor provided is in the form of .lib. Okay, and this is always provided either by your standard cell foundry, or you can say a standard cell vendor, or by the foundry that you're going to decide to choose. Okay. Now, what happens in this is, right, yesterday we had a discussion, correct, that ma'am, what is my MCMM, correct? I was stating that you don't get one lib. Okay. If you would look in your designs, there would be library related to all the different PVT coordinates. Okay, PVT stands for your process, voltage, and temperature. See what happens is, for example, let's correlate to a real world example, stating you are a person. Okay, now we have different seasons. Okay, in India we have this different kind of seasons. While if you go to Canada, there is only winter for around 10 months and then summer for 2 months. But for example, we are staying over here in India. There, let's say that winter is ongoing, right? In the winter season, you behave differently. Like you become more lethargic. You are in the mode of that every day. You are just having hot samosa and tea, always inside the blanket, correct? But when the summer comes, okay, now you don't want the hot tea, correct? In summer, no, I'm not sure if anyone's like to have a tea. Everyone would be in the like either should have a cold coffee or a coconut water, correct? You won't be even lethargic. You won't even like to sleep in the blanket, correct? So see, you are the same person, but you are behaving very differently in summer, winter, spring, autumn, rainy seasons, correct? Similarly, when your design consists of cells, right? When you have decided that I am going to use this cell, the cell would remain the same across your complete design. But the way it behaves, like the summer, winter, what I am saying, are your different PVT. Their PVT is nothing but your environment, your surroundings, right? How does it behave? So what happens is this timing library, you would have heard that there is a position called as library characterization, standard cell library characterization folks. They are being hired for doing this kind of a stuff. Okay. So what they do is like they have to characterize and provide this information in this liberty file. Okay, this is not something rocket science that it gets. They are doing this characterization. So they are taking each lot of standard cells. When we discussed, right, we can have within an AND gate, we can have different input, two cross one input AND gate, 3 cross 1, 5 cross 1. We can have different drive strength cells we can have them across different VT as well, correct? Different threshold voltage, low VT, high VT, SVT. So what happens is this library characterization team, right? They have their own softwares, okay? In general, we call them as a library compiler. Synopsys have their libgen compiler, Cadence have some different compilers. Okay, I'm not going in depth about it because I have never worked with library characterization team. Okay, but I have an overall knowledge that what they do is they take each and every cell and they note down the behavior of the cell. That how does this cell behave in, for example, if you look at the PVT, how P stands for process. There are three typical processes in which we define as slow, slow, typical, typical, fast, fast. So they'll validate how the cells behave in this process, how it behaves in the different voltages, right? You may be like your design is going to work on 1.2 volt, as I stated yesterday, right? That your design is intended to work on 1.2 volt, but it is not necessarily required that all the cells in your design will get 1.2 volt. If there is an IR drop due to some activities, there are high like flops surrounding them. So what happens is the voltage that is reaching your cell can degrade. So instead of now 1.2 volt, it might get just 1 volt. Okay, or sometimes if the power peaks up, the voltage bump is there. Okay, it can happen that instead of 1.2 volt, it might get 1.3 volt. Okay, so at a very high level, folks or this, they come up with this like what's the range of process or what's the range of voltage and temperature we should test this. Okay, so they only say that okay, I have a requirement that my chip should be functionable from at least 0.8 volt to 1.4 volt. Okay, I have very much great confidence that the voltage drop won't go beyond 0.8 volt and the voltage bump or the voltage spike won't even happen beyond 1.4 volt. Okay, so now we tell even the we tell this standard cell library team that okay, you have all the characterization for this to this. You have to tell them okay, with this is the temperature range from minus 130. I am trying to look at how till plus let's say 240 degrees Celsius. So you have to get it characterized within all. So they will give you all this kind of information in the form of library which is tested and characterized across all this kind of PVTs. Okay. Now what happens, they don't only even characterize it based on this PVT. Okay. Now what happens is, for example, you are the same person and for example, if the person, I give him 5 kgs of potato.
You are
Okay,
writing something?
no, I'm
Writing?
not writing actually something.
Okay, okay, fine.
Using the board.
If you want to write, you can write.
Sure, sure. Yeah. I'm just stating for example, right? I have stated like for example, if you have 5 kg of weight, I'm saying giving you 5 kg of potatoes and I'm saying that the person A to go and give it to the person B who is saying 10 kilometer away. Okay, now this person has the energy, it will take this 5 kg of potatoes and take it from A to B within let's say 10 minutes. I'm giving a hypothetical example, guys, won't say that within 10 minutes we can reach 10 kilometer. Hypothetical example just for your understanding. Okay, now what happens is instead of this 5 kg, now what happens is I stated there is a birthday ceremony of this person and he is making vada pav. So instead of 5 kg, we need to give the 10 kg potatoes. The person A has to now, instead of taking 5 kg of potatoes, have to take 10 kg of potatoes. Okay. Now you guys only tell me. The person has the energy, he is strong enough. But now for the same distance, right? Will he be able to cover in just 10 minutes? No, correct? Now, instead of 10 minutes, the person might take 15 minutes. So the same happens with the cell, okay? Within the cell, if you would have looked at upon, for example, if the fan out or the load increases, the cell delay increases, it degrades, right? If your input transition becomes bad, okay, your delay of the cell increases. As and when we'll go in detail, I'll explain you what slew, transitions, everything. These are all terminologies. But see, the same person now with the different weight, he took a longer time. Okay, so same happens with the cell, right? For example, if this is an AND gate, here instead of this kg, right? Whatever the load I have given in human terminology, this 5 kg of load or weight, what happens within this VLSI world, it is equivalent, the load is equivalent to your load capacitance, correct? When you say output load, you don't say it in terms of, load is measured in terms of capacitance, right? For example, if this cell, which is, let's say D1 is my AND gate 1, it is driving one buffer. Okay, it's fine. I am driving one buffer. I can deliver the amount of value which I have written. I have got it from my previous stages. Okay, the driver cells. Now let me say that instead of one buffer, it has to drive three different buffers. Okay, now what happened is, see, here the load increased. This became the first load. This became the second load. This became the third load. So what happens that once your output load capacitance has increased, now the cell will become slower. Just always try to correlate all the things, guys. I would just suggest, like, once you're doing it, try to visualize and correlate with your real world example so that you understand it. So then you don't have to, like, memorize it. Okay, load capacitance increases, delay increases. Why? Understand it. This is the way that once you appear for the interviews or any other examination, you will have it just clicked. Okay. Because in your real life, if your weight increases, your also delay increased, right? Similar happens with cells as well. Okay. So what the library characterization team does it also does it. Like, for example, if the input slew, right? If it goes bad, how will the cell output be? If the output load increases, how will be the cell be? So along with this PVT, they look at what are the various transitions made with respect to your input and how your load takes it. Okay. So just to sum up, you've understood that this library generation is done by the library characterization team, which is from the library vendor or the foundry. Okay. And this is then being used. See, this, what library is being used either in your synthesis. This library is also used for your STA when you're doing prime time. This is also used for your physical design, right? Yesterday, somebody asked me that every time will the Verilog net list be same? For example, we took an example of full adder XOR gate, correct? I stated no. If the tool found out that okay, there is a better version of a cell available, it can replace it so that it can be optimized with respect to PPA. Right? Now, for a human being, like you and me are talking, and I say, for example, man, I have to swap. See, my area is, let's say, the hypothetical example, don't take it with respect to this. My area is 1 micrometer square requirement and 10 micrometer square requirement, and I am going the budget, and it's now becoming around 11.2 micrometer square. Okay, this you and me are able to understand it. This constraints when it's given to the tool, right? The tool find out, okay, the person is not able to meet the area. Then what will it do? It will come into the library and search. Okay. Now you and me are understanding, if I swap 3D, whenever I say 3D, it means 3 drive strength. Okay. And 3D to and 2D. Okay. Now you and me understood, because we have a hypothetical concept. We have learned it that if you increase the drive strength, your area will increase, but you will gain on your timing. But how will the tool is stupid? Okay, you have to guide the tool. The tool doesn't believe on anything that is being mentioned over in the way we talk. Okay, the tool, what it does, it is smart. It will go look. Okay, now what? Now I said that we are not meeting in the terms of area. What it will do is, okay, instead of, let me see, if I convert and 3D to and 2D, okay, I am saving approximately 1.5 micrometer square. Okay, and I was just going above 1.2 micrometer square. So it will do this swapping. So what it will do is, it read your constraint that you have an area related constraint that I cannot go beyond this area. It comes into your library and checks it. So this information is available in your library. What? Area. Correct? You got this information of area. When I stated I am not able to meet my timing. So you got to know that you have different variety of VT flavor cells available in your design. So you and me understand it. Okay, if you transfer it from high VT to low VT, your timing will get met. Tool is like, let me check. I will go into the library. It will take, for example, if there is same variant, let's say I am giving as an 2D LVT, and there is something and 2D HVT. Okay. Now my design was having HVT and I was not able to meet my timing. Okay. Now we got to know that, okay, if I replace my HVT with LVT, I will be able to meet my setup timing. Let's say setup timing. So what this tool do is, right, it comes into the library and check what is the delay of LVT cell, what is the delay of HVT cell. Okay, the delay of HVT cell is, let's say, 1.5 ns, while the delay of LVT is just 1.2 ns. I am saving on 1.3 ns. The way, for example, my setup is going a slack by 0.1 ns. Okay, so I can use this. So the tool has its own way of understanding and validating it. It does not mean that I am just telling you swap it. Tool will go find it out. So tool got to know that, okay, the timing information is present in my logical library. Okay, I can use it. So you understood, right? The tool does you understood how does this input files are so much important, how the tool understands it. It first get the constraints. Okay, I have this constraint. Let me go into the library. Then it will read your library. So overall, when I'm explaining you this, the library contains, you can say, complete detailed information about your timing, your power, how your functional characteristics of all your standard cells. Okay. So I'll just try to give you about how does a timing library even looks like. Okay. Once we even go to the lab sessions, we'll open up the library from there as well. But as of now, let's try to see what from whatever snippet I have it. Okay. Now, this is a, like, I cannot copy paste it from any of the professional this and paste it. This is a reference I have just taken it from the net site, and just for your explanation, I'm going to depict it because this is an overall the same base. Whether vendor can change across, but this is how a framework of a timing library or a logical library looks like. Okay. So the first thing is, right, if you look at it, it states library. Okay, library, and it states something as name of library. Okay. Now when you say about, okay, name of library, now what happens is every industry standard will, whoever is a library vendor can have a different naming conventions. For example, if I am using I have taken this timing like logical library from, let's say, TSMC. Now within TSMC, I stated there are various tech nodes. It can be from 180 nanometer, we have come down to 5 nanometer, 3 nanometer, 2 nanometer. Let's say I'm using, I have decided that my tech node is going to be 5 nm. Okay. So they will have just a naming convention so that they are aware of what library is this about. So they'll have some naming convention as TSMC5 underscore standard cell underscore PVT corners related something. Okay. So the framework will start with something as library, and so that once you read it, you will just get to know, okay, this is related to tech node 5. This is all, it will contain all the standard cells, and there will be something related to on which PVT it has been working. Okay. Now, the second attribute or the parameter that is there, it's technology. Okay. Over here, if you look at it, is CMOS. Okay. There can, right now, PMOS and NMOS is not somewhere used. CMOS is the one which is used worldwide. But there can, for example, if the future, if you look at, there are different new technologies developed across. For example, Intel had a different kind of a FET, which is called as a ribbon FET. Okay, no, we are not going into detail about what are all those things, but yeah, there are different kind of technology. Just for your understanding, all the standard cells which are there in my design are built using CMOS. Okay, then there have something called as delay model. Okay, now if you look at delay model, correct? It tries to state as the table lookup. Okay. Uh, any one of you can just let me know how do you calculate delay in your real world? Any one of you?
I mean, in the real world, do you mean the cell delay, how we calculate?
Yeah.
Yeah, so based on this input transition and output load, in
Okay.
these two parameters, we'll vary the values in the input transition for different values, and also output load will vary with the values in the picofarad or something units of farad. So we'll interpolate or extrapolate the graph based on these two values, and we'll get some delay values of that particular cell, of that particular recipe of the cell.
Great. So it is dependent upon, see, every one of you would have looked at this example even when you're doing your control systems or your signal system, saying delta is equals to RC, right? This is a very famous equation used across all VLSI engineers, right? Delta equals to RC. Okay. So now what happens is this R is nothing but your input transitions. How is your, based upon, this is not R resistance, this is kind of how is your input transition happening. This is getting affected by your resistance, right? If you use the lower metal layer, it will have higher resistance. If you use higher metal layer, but now as of now, for our simple understanding, consider it as how is your input transitions. Okay. And then C is nothing but your load. As I stated, right? If you increase your capacitance or if you increase your load, your delay will increase. Okay. So all the delay values across any of the cells, whether it can be a standard cell or it is a combination cells or is it a sequential cells, every delay present in this library is going to be in the form of table lookup. Some industry call it as LUT. If you get this terminology right, don't get confused. It is called as lookup table. Okay. Now this table is of, if you look at it, right, this is depending upon two parameters. Okay. So it is also up, for example, let me say, for example, here I am going to give my R values. Here I am going to give my C values. So let's say 1, 2, 3, 4. Okay, these are my, let's say these are my resistance of 1 kilo ohm, 2 kilo ohm, 3 kilo ohm. Okay, and then there is going to be capacitance, let's say 0.1 till 0.5. Okay, then there comes a value. Okay, there is value x1, x2, x3. Let me say now I have three values. Okay, 0.1, 0.2, 0.5 are there. Now what happens? There is y1. Similarly, everything, let's say, and for here we have four values till z3. Okay. Now, how does any of the delay gets calculated is, right? It looks, for example, how is my input transitions? And let us find that if this is the value it gets, okay, my input transition is this much. How is my capacitive load? Okay, find out I am in this one. Let's say this value over here was something related to M1. So how does the tool substitute when you're doing STA, right? Or you're doing any timing analysis? If you look at the timing report, I'll go it in that later section, but if you would have done in your college projects or something, you will have that each cell delay is mentioned. Okay, cell delay is not a kind of a hard-coded value. Okay, it depends upon two parameters and how they vary. It it calculates into the delay. Okay, so now you got, okay, this is something like this is my input transition, this is my this. The tool will go and find out, okay, M1 value, and then cell delay will be given as M1. Now what happens is, for example, let's say your value was something between 1 to 2, it was something related to 1.5 as your input transition. And between 1.2 to 1.21, the value was something related to 0.15. Okay. So now tool is not something, oh man, there is no values. I am not sure what will be the delay. So tool knows an algorithm of interpolating or extrapolating. Okay. So this interpolating is, okay, if I found the values are within the ranges which are being described, I have an algorithm. I can do some scaling method. I'm not going to explain you how does the tool does this. I'm just giving a very brief overview. What the tool does it, okay, I have a value between 1 to 2 and 0.1 to 0.2. I will come down to a scaling factor and analyze it, and I will have the cell value. So then then the tool gets to know, okay, this is my delay value. If any ranges go out of this, it will try to extrapolate it. Okay, so you understood. So all the delay values within your this library is going to be in the form of LUT or a lookup table. So it is trying to say that this is the way I am going to be present. Okay. Then there is something that whenever your compiler generates this what do you call it, library, it has a date of creation. There is a revision number. See what happens is when you are developing anything, right? See, every time, let's say that now iPhone 17 is going to get released. There was previous also, there were a lot of versions, right? 16, 15, 14, 13. Every time what they are trying to do is they are trying to improvise it, right? They are going to make their camera better or their processing speed better, correct? So every time they are going to make it better and better. Nobody is going to do it, let me degrade it. So same happens, right? When these standard cell library team or the vendor or the foundry are trying to make the cells, right? They are trying to make it in a more optimized way. Okay. So every time what happens is, once let's say that they have first built something, let's say it's revision 1. They might come, okay, we have got a newer version with better features, that they can give it to the revision number 2. So this is not something that is too much use for us, but I'm just giving you like this has something related to it. Okay. Now there is something which is called as units. If you look at it, right? Now, for example, if they publish in front of everything like 1.2 volt, temperature in Celsius or Fahrenheit, process in this, so it will take a lot of space, right? So what they are doing it, man, we are pasting the units at the top. Okay. So whatever the time, if you look, whatever is in the delay, okay, or whatever, wherever is the timing units, it will always be in nanoseconds. Okay. So wherever you read just the value, so just say that the value of this time is, let's say 50. So understand that this is 50 ns. Okay. Now they're saying that in terms of power, I will be in a picowatt. When you're talking in terms of voltage, I will be in terms of volt. Okay, so it gives the unit for all this thing. If you look at it, right, femtofarad, micro amperes, it gives the unit of all the things which are present in your design. Okay, now there comes it like it try to state, okay, see, this library is for some PVT corners. Okay, so they are stating, okay, I am being characterized for this voltage, this temperature, this process. Okay, industry standard follows a process in terms of a number. When we understand it, we give it as typical, slow, fast, or something like that. When an industry does it, with the library compiler mostly give it as a nominal process, which is typical. Nominal is, you can also call typical as nominal. It will give you as 1. For example, let's say if this is a line like 1.0, this is my typical, or you call it as nominal. Okay. Now there is something which is slow and fast. What happens is the industry standard, when normally when I have looked into the library, right, when there is something which is fast, right, they will give it as for example 0.9. I'm not saying this is a hard something, but okay, you will look at this process value can be 0.9. You can open up the library. There can be a different vendors using different convention, but something is, if they're using 1.2, this states slow. Okay, this states fast, this states typical. They are the vendor which I have worked upon, maybe they are trying to state because if the process is faster, it means it takes lesser delay. Okay, so this is why they are using it, but just for our convention, you understood. Okay, anyways, at the down, if you come, there is something which is written over here, typical. There you will get either value as typical nominal, or you will get it as slow, or you will get it as fast. Okay. Again, so there are different things which are mentioned, that operating condition, I have this process, temperature, voltage. Okay. So you understood that within this, you'll have your information related to your, what is your PVT corners, on what is your technology, what is the revision, and what are the different units of your this related to all your current, voltage, power. Now we'll go in detail about within, let's see, this was an header section of your library. Okay, now let's come to within this, there will be lot of cells, right? If you would have ever opened guys the library, it runs in lakhs of lines. Okay, more than 20 lakhs or 15 lakhs of lines are there. Okay, this, the format I'm trying to explain is the just a framework, so that you understand that how does the tool go and what does it search for and then come. Okay, so first thing, if you look at it, right, it's mentioned cell. Okay, now for example, if you open up, what happens is, if you open up a library, and I'm just stating that I have given you this library and I am telling you how many cells are there. Okay, so what they have done is, you can, I'm not sure if you have used grep commands, and there are a lot of things. Okay, if you're working with the VI editor, there is a command to do like just grep the cell and find out how many instances are there. Okay, so that it becomes easy for you. So they have also mentioned that this is the cell. Okay, so they will use a keyword as cell, so that every time you press or try to find out the cell, you will get, okay, how many cells are there. Now this is your cell name. Okay, this is your cell name. I'm taking about, somebody asked me a question yesterday, reference name, inst name. This is the cell ref name. All the names which are present in your library are the ref name. Once you use them in your design, you will have it in your netlist in the form of instance name. A1 and then your ref name is and 2 cross 1. Okay, so this whatever is present in your library are the ref name of that cell. Okay, now once you read it, okay, every industry standard follows their own format for this cell naming. Okay, there is no standard cell format naming convention followed across all the vendors. Okay, now when I read it, I understand it from basic conventions. It is an AND gate, definitely. It is 2 cross 1. Okay, now this since this example I am not, because I am not going to write the library, I took it from the net. In real world, when I take it from any TSMC or Intel node, it will have something as AND 2 cross 1. It will have drive strength also mentioned in it. Let's say it will have wording as 3D, and then it can have your, what I stated, right, your VT. So as of now, we are understanding from this, okay, I am an AND cell with 2 cross 1. Okay, now you don't have to worry about what is GS005, 006. These are the library characterization team has done something to give a kind of this how many attributes are there. They are giving it as a kind of a number. Okay, 005 they are using it for giving power information. If you look at 6, right, all the power related information is given in 006. So this is something that library team is going to use for their analysis, that how many attributes are being defined. Okay, so the first thing that I'm coming under the cell section. Okay, now this cell has something as mentioned as PG pin. Okay, PG pin VDD. Okay, PG is like power ground pin. Okay, now within this, okay, this is whenever this opens up and this closes up, all things are related to this PG pin. So it is time to say that, okay, my voltage name is V. Okay, now every time this V you don't need to understand, because I have understood that my operating voltage is going to be always 1.2 volt, right? So that's why they are not writing everywhere, because see, if there are hundreds of cells, this will take a lot of time. So they are instead writing, okay, I understood I am from 1.2 volt. So my voltage is this. Now PG type. There it is mentioned as primary power. Okay. For example, those who attended my low power lectures, right? You would have gone through some special cells which are called as isolation cells, level shifter cells, always on buffers. Okay. There, when I was explaining you about let us take an example of isolation cells, right? Isolation cell is a special kind of a cell that is being used when your signal is crossing from less on domain to higher on domain. I'll have a lecture later onwards to explain in detail about what all these things. But let's say there are two blocks operating on same voltage, but one is always on. Let me say always on, I'll denote it as AON, and PG is like power gated. Okay, don't take it as power ground. This is PG, means this block within my same block. Okay, this is the same block, but within this I have two different blocks, which are one is always on, one is power gated. What happens is there is a signal. Let's say there is a signal A which is getting transferred from power gated to always on. So in this case, right, for example, if this power gated, it turns off and it is giving a real value to a cell which is sitting in the always on, right? Because since the power is being turned off, I'm not sure how will the cell behave, right? It may go to a lower value, but the data which was being transferred was 1. Okay, so we do an intentionally, we put a special type of a cell, let us call it as isolation cell. Okay, so we can clamp it to either value 1 or value 0. This is being decided by your UPF and everything. Okay, now let's say that, okay, there is a cell. Now this cell is sitting in this domain. Okay, now for example, see, all the cells will have power ground pin. No cell is going to be there without power ground pin. Okay, now let's say it had one power pin, one ground pin. Okay, since the power of this block is gone, right? So it means this power is also gone. So this isolation cell is not getting the power to deliver the data to the always on block, right? So what happens is there is a terminology over here which is called as MPP, which is called as multi-power pin kind of a cells. These cells have an additional extra PG. Okay, so this PG, when you will go and if you look at the library of these kind of a cells, right, along with this primary power, they will have something which is called as secondary power, and this power has to come from always on domain. Okay, because see, this power is never going to be turned off. Okay, so what happens is even if this power is turned off, the cell will be still alive, right? It is not going to in dead mode, because it is getting the power from the secondary source. Okay, so if you look at the kind of these cells which are MPP cells, multi-power pins. So they will have something along with primary power, they will have secondary power, and they will have their naming convention as beyond or whatever the industry wants to follow it, they will have something as secondary power. I just wanted to give you a bifurcation, why primary power, why secondary power. Okay. Then comes next pin is VSS. Okay. We as an individual, when we are studying throughout, we always call it as ground. Okay. This is something within VLSI, we don't call it as GND or ground, we call it as VSS or substrate or sometimes. Okay. This is for your normal understanding, this is equivalent to ground. Okay. So it will have an information, okay, I am VSS. VSS is always tied to 0 volt. Okay. This is also primary ground. Okay. Okay. Now there comes a something which is called as, if you look at over here, is scaling factors. See what happens is scaling factor. Okay. Now I stated that the library team has to work and it has to generate the library across all corners. Let me say, for example, if you have 3 different process, right? Slow, fast, typical. You have, let's say, 5 different voltages, and let's say minimally we are keeping 2 different temperatures. Look at the combinations that are possible for the library team to characterize it, right? So what happens is, right, nowadays it doesn't happen. We ask the library characterization it. Earlier, what could have happened, right? They used to characterize it in one corner, one PVT value. Okay, let's say they took very, let's say, typical corner, 1.25 125 as temperature, 1.2 as your voltage. Okay, and they did the characterization of this 100 cells. Now what happens is, the library team is going to give you this library, and along with this, now this factor is, right, this will see here, this is value, this is mentioned as just this cell and mentioned as factors. Earlier what it used to happen, right, for example, if you're not asking the library team to give all the characterization, in this section they will give you some value over here, saying that, for example, if you want to characterize it, let's say this was being done, right, let's say this was being characterized at this process, this V and this T. If you want to go, instead of 1.2 volt, if you want to go at, let's say 1 volt. Okay, now what will give you, if you want to characterize it for process 125 degree temperature and 1 volt, the scaling factor is, let's say, 1.25. Okay, I'll explain you just. Okay, so instead of this, now we will have something as 1.25. Okay, why? See what happens is, now instead of 1.2 volt, I am checking my design at 1 volt. Okay, I have not asked the characterization library team to give me all the library. Just give me a scaling factor, I am okay with it. Okay, so scaling team will does, okay sir, we will give you a scaling factor. Now what happens is, if you all know, right, if your voltage, does any one of you know how's the relation between PVT versus delay?
Yes.
Okay, you guys.
Okay, you wanted me to tell or else?
Okay, guys, is any only the one person answering or everyone? This is your basic BTech, man. We have never looked at how does a PVT corner looks like. How does the PVT varies with respect to your delay?
Yes, ma'am.
Let me see. Okay. See how many folks are aware. Like, people are not sleeping, right? For example, Venkat, are you there?
Yes, ma'am.
Okay, Venkat, you are only speaking, correct?
No. I don't want you to explain, ma'am. I think I'm saying that I know some of the relationship. So are you thinking that you want me to explain?
Just explain me. For example, this is my voltage and this is my delay. Every time I will be explaining delay in terms of this delta. Okay. Now, Venkat, how will be the graph of voltage relationship with respect to delay?
Yeah, if it was lower voltage, then higher delay. If it is higher voltage, then lower delay. I mean, inverse.
So there is an inverse relationship between V and D, and instead of me drawing a straight curve, it's not exactly that you have like this. You have something like this curve. Okay, this is the valid curve. Okay, this is the hypothetical curve that it approximately. This something not completely new. Okay, thank you, Venkat.
Okay.
Okay, so guys, what happens is, right, let's say this is from 1 volt. I am going, let's say from 0.1 volt, I am going till 1.2 volt. Okay. Now, when I was giving you the example, the library which we had was being characterized in 1.2 volt, right? And I am stating that I want to look at what it will behave at 1 volt. Now, see, I am reducing the voltage, correct? Reducing the voltage means, if I'm reducing the voltage, it means I'm increasing the delay. So what happens is, let's say when 1.2 voltage was there, the delay of one of my cell was 100 picosecond, let's say 100 ps. It was 100 ps, okay? PS and let's consider anything. Now what happened is there was a mention of scaling factor. I stated you that the scaling factor will mention over there will be 1.25. So you have to do a very simple calculation. Whatever is the value which is being provided, I will multiply it with 1.25. Okay, so what happens is now my delay would be 125 ps, which is correct, right? Because voltage is decreasing, delay will increase. Okay, so this is the way that the library characterization team will come to the scaling factor. The scaling factor has to be provided from their end. Similarly, so you just have to use the scaling factor, multiply with across all your power values or with your timing related stuffs. Okay, scaling factor cannot be multiplied with area related stuff, right? Cell area will remain same even if you increase or decrease the voltage. Okay, with related to only timing and power, you need to just do a simple calculation, which is a multiplication. Okay, whatever is in the nominal multiplied your scaling factor. Okay.
Hello.
Yeah.
Yeah, I have a small doubt. So how could the scaling factor be a constant? Because we have a curve which is exponential, right? So how
See,
can a scaling factor
this
be
is not
constant?
exactly the value for this. See, what happens is when you're doing an early project, early analysis project, right? What the team at high level does it, right? The library characterization team might take some time. It's been saying that, sir, we have something related to nominal stages. We have it. In case you want to use it, we are just giving you a rough estimates.
Okay.
Okay. So if you want to use it, you go with your early analysis. See, the project cycle in the companies goes very fast, right? Once the time all the libraries are available, it is fine. But if you're doing an early analysis, you say, okay, I am fine, my tool will understand it and it will do a rough calculations. This is not the proper calculations. Once you're doing STA, right, which is the time when you're doing prime time, it's the final sign off. You will include all the libraries, correct? But for an early debug and analysis in the earlier stages, you can use a scaling factor. Okay,
Yeah.
but this scaling factor is also not a random value. Even the library team has some algorithm to decide it. Okay, I just give you a rough estimate of 1.25. It can be just 1.08. Okay, so this number also has to be calculated from their end. It just have very plus or minus little bit of difference, but yeah, very close to the nearby value.
Yeah. Got it.
Okay.
Yeah.
Fine. And this is if I'm drawing it, let me get somebody. Diptanu, are you there?
Yes, ma'am.
Okay, Diptanu. Okay, Diptanu, can you answer me? How does I'll give you a simple question. How does the process vary with respect to delay?
Okay. So slow process will have higher delay. Typical process, medium delay, and fast process will have lower delay. So if we code 3 points on the process, then we can able to slow process, medium, typical, and high. Then it will be inverse again.
Okay, so you are saying as the process becomes faster, the delay will.
Delay will decrease.
But why I'm seeing is it there is a glitch? I'm seeing Venkata speaking, but where is Diptanu? I'm not able to see.
So
He just
sorry,
left.
ma'am.
Diptanu is itself was speaking, right? I was not able to see you. I was seeing Venkat answering the question. Fine. So this is also the curve for process versus delay, correct? As the process becomes faster, your delay reduces. Correct? Fine. Let me find out someone which is a typical question. Let me see. Shiva, are you there? I just want that everyone should be aware and available in the meeting. This is not something that I am speaking. I want you guys to be also interactive. Okay, Shiva, are you there? Shiva, did you went for tea break? Guys, this is not something which is looks good, right? If you are there in the lecture, please be available. Try to unmute yourself, answer it. Even if you're not able to answer it, see, this is not something that I am hiring you, right? This is something I'm preparing you for being getting hired, correct? Ravichand, are you there? Guys, am I audible?
Yes, yes, yes.
So like I note down the folks, right, who are not present over here, and they'll have to give attempt a surprise test. Okay, I'm noting down the name. Shiva, Ravichand. Okay, these folks are not available over here. They are just logged in and went away someday. Okay, let me see. Lata, are you there?
Yes, ma'am.
Okay, Lata. Fine. Now let's see. I want to give you the process has happened, the voltage has happened. Now there is something with respect to temperature. Can you just let me how does the temperature helps with respect to the delay?
Yeah. So what happens is, so if you increase the
Lata,
temperature, right? Hello?
is this Lata?
No, sorry, sorry.
Ma'am, it is linear, I think.
Linear. See, this is also way to draw a linear. This is also way to draw a linear. This is also way linear. How do you want to give me?
Slack, second one.
Second one. We are
Yeah.
trying to state as the temperature. Okay, let's listen. As the temperature increases, what happens, and if the temperature decreases, what happens? Just give me a simple form.
No, I think temperature increases, then resistance will increases. Then tau equal to RC, then tau will also delay will also increase.
Guys, Lata, are you a lady or you're a gentleman? Am I
Sorry,
getting different kind of voices? The question has been asked to Lata, right? Lata, where did you go?
I'm still here, ma'am.
Okay, so Lata, for you, let's say for you, how do you feel? Please say either it will increase or decrease. There is possibility. It won't remain constant. Even if your answer is wrong, no worries. I am there to explain it, correct?
Yeah, ma'am.
So if your temperature increases, what will happen?
Temperature increases, the mobility of electrons are increased, so resistance will be increase, I think.
So the same. With delay, what will happen? Delay will increase. Your cell delay will increase, or your cell delay will decrease.
Cell delay is increase in higher nodes, lower nodes.
You're saying higher. Your temperature is increasing, your delay is increasing. Your temperature is decreasing, your delay is decreasing. Who was the other person who was in the middle who was trying to answer? Can you just unmute yourself and do you agree with this thing?
Yes. Yes. So if your temperature increases, right? So what happens is there will be collisions. So there will be collisions in your structure. So what happens is mobility of your electrons will decrease. So your delay will increase.
Okay, so this is
So
a very hot topic
correct.
which
So
is
that
being
one is correct.
there is a very hot topic which is being trending. There is a concept of temperature inversion.
Temperature inversion. Yeah, ma'am.
Okay. So what happens is it was not too much familiar at higher technology. Let's say 180 nanometer. At that time, this was not being there. Now we have moved to such a lower technology nodes, right? I'm not going to explain you in detail because that's not the part of this lecture. Earlier, this used to be hold true. Okay, that if your temperature increases, your delay is going to increase, and this was an
Increase.
increasing linear curve. Okay, but
Okay.
since we have come down to the lower deep technology, sub-micron technology node, right? There is a concept of, you go and read it over there. There is a concept of temperature inversion. And now if your temperature is increasing, this is helping your cell delay. Okay. And now all the designs that we are working upon have this. Nobody's right now in the industry is working on one. It's Below 65 or 70 nanometer, I think this temperature inversion concept is there. So you just have a look how this topic is. But nowadays, if your temperature increases, your delay will decrease. Okay. So this is the complete correlation, guys. This is the basic funda that you should know, right? That how does the PVT matters, right? Because when you're going to analyze your reports, when you're doing a timing analysis, right? You're looking exactly as stated, right? Yesterday, if you look at the same path from like start point, end point are same, two paths are same, but you're looking at two different corners. The cell delay is going to be different, right? Because your voltage have changed or your temperature would have been changed, right? So if you don't believe me, don't believe my words. If you have the library and if you have the STA setup or something in your college or somebody, take an exact start point, end point, through path, even keep the process and the temperature same, just take two different voltages. That's very simple. Take two different voltages and compare that how is the cell delay. Just take this cell because having this much delay, now in this voltage, how much is the delay. You'll only just get to know that what's the correlation. Okay, fine. I'll go ahead. Okay. So fine. Now we are like, we had something, okay, with related to scaling factors. Now there's something, right? I told you. How will the tool know? I am just stating you that, okay, we can go and have look for a cell with the lower area. Tool will come, search what is the area parameter. It will search, okay, this is the cell having this much area. Yeah, I will go and look at like what, for example, 3D cell, how much area does it have? Okay. So this is where the parameters that the tool tries to come and look into it. Okay. Now there is something which is leakage power. Okay. Now say that going ahead further, last time also I gave you when I took a low power lecture, I gave you examples of different types of power dissipations and everything. Right now the intention of this lecture is not about power. I'm just stating that this power, okay, leakage power, dynamic power, the leakage power information is present in this format. Okay, dynamic power calculation requires your switching activities and all other various factors, but the leakage power is dependent upon the cell functionality. Okay, now this value is also not a simple single value. Okay, if you look at it, okay, there will be different values. For example, let's say it is trying to say, okay, the power will be always with respect to, it is trying to say VDD. Okay, I said because right now you, as of now, you have only one primary power pin. There can be multi-power pin, which I stated, right? It can have VDD1, VDD2. Okay, so now it's saying that with respect to this power pin, I am stating, now it's saying when, this is a condition, okay? When in one apostrophe into. See, you are understanding that this is an AND function. Okay, it is stating that when in, see, anything in the bar over here means it is like, it is trying to say something like this one. Okay, this is low values. Okay, bar always means low value and one without bar means it's high. So it is stating that whenever your input is low in one, okay, this is very simple example I'm trying to state. This is my AND gate. Here instead of AB, it is trying to say in one, in two. Okay, the output can be something that's one. So it is trying to say, okay, when in1 is making a low transition, in2 is also at low, I will have this much value of leakage power. Okay, now it comes. See, two inputs are there, then you are very much aware that you will have four different combinations, right? 0, 0, 0, 1, 1, 0, 1, 1. So it has mentioned all these combinations over here, okay? That, okay, if I have these all combinations, these are the things, these are the values, okay, that they will have. This library characterization team have very, it's also in different, complete understanding that you need to do. They do this characterization and the simulations they have to do, okay? And then the simulation results are being jotted over here. So it will give you the values like if this pin is making a high transition, this pin is making lower transition. Okay, this is my leakage value. You understood? Okay, the header section of your library stating, okay, what is the name, when I was created revision, what are my different units, and what are my PVT corners. Then you come inside the cell sections and you look. See, this is very smaller sections which I have denoted. There will be approximately more than 50 plus parameters which are being defined for individual cells. As and when, for example, you go into a sequential cells, okay, as it has a lot of things, it will have different kind of attributes. So for very basic understanding, I gave you first a cell of an AND gate. it has participant related information, it has information about what's its area, then what is its leakage power. Okay, then before going into it, okay, there is something, let's just give me a moment. Okay, sorry. So I said now we have looked upon power, area. Now there is something which is still remaining is, which is very important, is timing, correct? The timing information is also to be expected to be present in the library, correct? So how this information is being provided? At the start itself, right, I said that your delay will be in the form of lookup table, correct? So the input, yeah. Hari, are you there? Hari, are you there?
Yeah. Tell me.
No, I'm asking Hari. I think the folks have joined, but I'm not sure if they are really participating over here. Okay, Ravi Teja, are you there? Let's see. Guys, please unmute yourself. At least say yes. I'm not going to throw any.
Yes, ma'am.
Okay, Ravi, you are there, right? So, Ravi, at the start, I said like your delay would be a combination of two parameters, lookup table, correct? What are those two parameters?
Hello.
Yeah, Ravi, what are the two different parameters based on which your cell delay is calculated? Let's say very simple cell delay. So, what are the two different parameters it needs to look for?
Sorry.
Ravi, are you answering it? I hear you.
No, ma'am.
Okay, so you missed it. I explained, right, what a table lookup looks like, right? The person also answered it, interpolation, extrapolation, how do the tool calculate, right? Guys, please, whenever you're in the lecture, please keep your ears open. And if you have not understood it, you can jot down at the end. I'll try to explain it one more time. Won't be something that I am explaining and you are not in the mode to grab it, okay? So, okay. So now what happens is, right, let's say I use the terminology input transition, okay, and there is something output capacitance or output load, okay. Now this word transition, right, it is used with different terminology which is called as slew, okay, slew, not skew, okay. Guys, don't get confused with skew and slew. I am taking the word as slew, okay. Now what happens is, how, see, when I'm saying the tool has this much value of input transition, or what is this input slew, the tool have to do its calculation, okay. How does the tool does calculation is done through a mechanism of slew, okay. Let me show you a diagram. Okay, let me move on to the next slide. Okay, you would have studied this all in your control systems, signal systems in your BTech, right? So now what happens is, right, when you have a signal, right, when you draw it, for example, when you are drawing it a very hypothetical or an ideal case, right, you draw anything, for example, if you're drawing data also, or whether you're drawing a clock, you always show it as a straight line, okay, rising edge, falling edge, but the real world doesn't happen like this, okay. The signal never makes a transition from 0 to 1 in 0 seconds, right? It takes some amount of time. So this is where, how does a real, either a data signal propagation or your clock signal propagation looks like, okay. Now, this is the way. This is, you are explaining, this is your rising edge, this is your falling edge. Okay. Now, how does the tool does its input transition calculation? Okay. It takes, okay, if the way my signal is propagating is in this format, every industry standard has a different way. Let me say that I will say the input slew is the time taken by my cell to move, to reach its outputs from 10% to 90%. Some company will take it in the format of like, this is the input, this is the amount of time which is required for this, which is required by the cell to make its transition from 20% to 80%. Nominally, the most of the industry standard either take it from 20 to 80 or they take it from 30 to 70. Okay. So see, when we were looking, our design was characterized for 1.2 volt. Okay. Let's say your maximum voltage that you can transfer it from 0 volt to 1.2 volt. Okay. So now it says that, for example, I am taking it from 30 to 70%. Let me say that I am characterizing it and I am the team and I am doing it from for the signal to make the transition from 30% of its initial value to 70% of its final value. How much time does it take? That is your input slew. Okay, that can happen for your rising edge. That has to even happen for your falling edge. Okay. Now, when you calculate the propagation delay, right? See, it says that how much when an input made a transition and it reached 50% at, let's say, 1 ns. So when the input was made, achieved its 50% value at 1 ns, how much time did the output at Y pin when you are checking it, right? At Y pin, it took around 1.2 ns. So it took roughly around 0.2 ns for this to reach from here to here. So that is the way that internally they are calculating this delays. Okay. So that is why it happens. Like, for example, if you look at your library, I have not shown in the library initially, the library will have like, see, I am calculating the delay based upon the slew values from 30 to 70. See, I took it from 30 to 70. People can take it from 25 to 75, 20 to 80, 10 to 90. So they will mention this. Okay, this are all the characterization even mentioned in the library. See, I cannot put the complete library picture over here. I'm just trying to maintain that these slew values, okay, are mentioned in your library so that you understand that the library characterization team has taken the transition from 25 to 75% and came up to this value. Okay, as I said that for rising edge, let's say, okay, this is the rising. So this 25 is your lower bucket and 75 is your upper bucket. When there is a falling edge, correct? Like this one, this falling edge. Okay, this will also have an upper threshold, lower threshold. So this is the way that the tool will calculate the transition time. I'm not saying delay. This is your transition time, or what you call it in normal VLSI world is slew. How is my input slew? Is it my input slew good? Is my input slew bad? Right? So this is the way the tool does the calculation of input slew. Once this slew information is present and whatever is I finally stated, your output capacitance load is present, tool will calculate your cell delay. Okay. So input transition or slew and your final load capacitance. Okay. Let me just move to the diagram. Okay. Now, this is, if you look right, I had a cell. We started with AND cell, right? So now I am at set output pin. Okay, pin Z. Okay. Now you look at it, it has something as direction. The timing, the input pins, right? They would also have a direction as input. Okay. Now pin Z has a direction as output. Okay. Now there you see there is a bucket which is available for timing, correct? Okay. So here is the complete timing related information. Okay. Now this information, it is trying to say that, see, instead of A1 or we had in. Okay. Now this example where I took it, it could have been of cell AB. They would have taken A or B as input. Let's consider that A and this is the kind of my gate. This is Z, this is A and B. So now I am saying that my input A, how is it affecting my delay at Z bit? Okay. Now there is a timing type. Okay, I stated. If you go and look at your sequential, it will have something related to sequential. If it is all combinations, then it will have something related to combination. Now, if you look at it, it has a section of cell rise. Okay, it is trying to say that when my signal is making a rise transition, okay, when my signal is making a rise transition, okay, how will be my delay values? Okay, so it is saying that how is my input transition time, how is my output capacitance load. Okay, this is the index 1, this is the index 2. Okay, every time it is not necessary that within the library you will have something as mentioned input transition time or output load at the start itself, right, where we saw that it will be in a lookup table. They give a brief description whenever they are referring that index 1 it will be related to something this index 2, so that they don't have to repeat it across the library. Okay. As for now, your reference, I have mentioned it. It's not necessary that it will be present. Okay. Now, if you look at it, if you have a transition of 0.02 and a capacitive load of 0.01, your delay value will be 0.03 ns. Okay, ns why? Because at the start you have mentioned the units. Okay, now if there is something between 0.05 and 0.05, all this combination, right? This is a matrix of 4 cross 4, right? 1, 2, 3, 4, 1, 2, 3, 4. So there are total 16 values which are present over here. What will happen is, right, if your values which is there between the range for input transition is between 0.02 to 0.2, and the values not mentioned over here, it will try to interpolate. If values goes beyond something, it will try to extrapolate, and it will get you a delay values. Okay, so cell delay is never a fixed value, right? Okay, there is an AND gate and it will always have 3 ns delay. No, it will be a form of lookup table, and it has to be input transition versus output loads. Similarly, it can happen that in the A pin can have, instead of rising transition, it can have a falling transition. It is trying to go from 1 to 0. So it will try to state, okay, this is my cell fall, this is my delay template, and this is my input and this, and it will have a values. This is all with respect to pin A. There, same thing will happen with respect to pin B. Okay. Now, there is a very simple funda that I feel like when you would have drawn, I think, the graph for the cell delay for your CMOS, just say, let's say basic CMOS, when you have drawn it, the way you used to draw, like it was kind of something as like this was your rise time delay and something as related to fall time delay. This was a very hot concept when we were in your engineering, right? That why is this fall time very less and compared to why is the rise time? If you have learned semiconductor physics in depth, right? You know, right? Guys, can anyone answer it if you're able to recall it? You have looked at this graph, right? It might not be there, but
Yes,
see,
ma'am.
this is the, pardon?
Yes, ma'am. We have looked at it.
Looked at this graph, right? So whenever you're drawing a charging, the way the, guys, if you're able to recall your CMOS, I'm speaking of. This is your PMOS, this is your NMOS. Very used to be a basic questions like PMOS takes a lot of charging time, NMOS doesn't take a lot of charging time. That's why the fault transition is very quick, right? For example, see, for charging to go from 0 to 1, it almost took, let's say, it almost took 5 ns. But for fault time, it almost roughly, I can say, correlating it to 3 ns. Okay.
Ma'am, because that mobility issues of holes and electrons.
Your
Yeah.
mobility of electrons is more, so that's why discharging time will
It
be
is
less.
charging time is high.
Charging time is more.
So this is why whenever your cell move, it's make a rising transition. See, if you look at it, right? I have kept the same, like I have not kept the library itself has 0.02 as your input transition and output as 0.01 load. But if you look at this value, right? When you're giving it as a rise time, right? Whenever a cell is making a high transition, so what happens is the PMOS becomes active and it has to charge it. So it takes a bit amount of more time. If you look at the same value at over here, right? The way it has been followed, okay? See, this is the way you need to correlate your concept with the library, right? So if you look at it, the values over here is not 0.03 ns. It's a bit less. Okay, I have made it from 5 to 3. It's not that much. It's 0.01. All the values that you look at it, right? 0.12 has come down to 0.10. The final value, which was for 0.2 plus 0.2 from 45, 450.45 ns, it has come down to 0.035 ns. So what happens is that fall time is always quicker as compared to the rise time. So this is something that I want you to correlate, okay? That whatever concepts you have learned, try to look into the library and correlate it with it. Okay. So this timing information is always present for all the cells in your design, whether it's a combinational cells or it's a sequential cells. Okay. Sequential cells will have a lot of different kind of timing arcs. Okay. But this is, I have explained you one timing related to your AND gate. Okay. Now going ahead, we have something as related to, I'm giving one more example, pin 1, pin 2. Here I wanted to explain you about, okay. See, timing direction is output, combination timing type. Then there is something which is called as, which is also one of the topics, which is like timing sense. Okay, you guys would have, I'm not sure if you would have heard about the concept of unnateness, or you call it as uniqueness.
Yes,
Okay.
ma'am.
Every combinational cells, right? It will have an information in the time of uniqueness. While if you go in the sequential cell, right? There is no sequential cell won't have a concept of timing sense. It will have either setup, hold, recovery. That's all the art that will go once forward. I'll explain you. But as of now, when you're comparing and considering this combinational cell, right? So you have to understand that what is unnateness. Okay, let me take a very common example. Let me say I am having an AND gate. Okay, what's the combination 0 0 0 1 1 0 1 1? What will be the output? This is an AND gate. Okay, what will be the output? Guys, anyone you unmute? I'll take a water break.
0001.
When any of the input is 0, output is definitely going to be 0. When both the input is 1, your output will be 1. Okay. Now, to understand the unnateness, what happens is, right? For example, let's say that I am keeping A as constant 0. A is not making a transition, it is stuck to 0. Now, if you look at B, okay, now B is making a transition. Let's say it is going from, earlier it was 0 0, now I'm moving to 0 1. So B is making a transition from 0 to 1. Now, if you look at the output, correct? Is the output making any transition? No, correct?
No change.
Earlier also 0, now also 0. So this is something which is called as no change. Okay. Now let's take another example. Let me step the output A to 1. Okay, and let's again I'm changing B. B is changing from 0 to 1. How is my output changing? If B is
0 to
changing
1.
from 0 to 1, I'm saying it is rising. 0 to 1 means I'm having a rising. How is my output changing? It is also going from 0 to 1, correct? Rising. Okay, so if my input is changing its transition from 0 to 1, and if my output shows no change, or if I'm rising and the output is also rising, let's take a reverse case. Okay, let me keep this also as 1. Okay, now instead of me going from 1 to 0, let me say that, okay, now from 1 to 0 I want to go to 1 to 0, which is fall, right? How will the output change? It will also go to
Those
fall,
fall.
correct? Okay. So the definition, if you would have studied and look in theoretical concept, right? If your input is rising and your output is also rising or making a no change, and if your input is falling and your output is falling, you would have heard the statement, right? Related to unnateness, correct? This is
Yes, ma'am.
something I have correlated with the example. If your input changes from rising changes to rise and your output is either no change or rising, then it is called as positive unit. If your input is changing, falling from 1 to 0, your output is either showing a no change or it's also falling. Okay, this is called as positive unnateness. Very simple, right? Because if your input is also rising, your output can either rise or it can show no change. If your input is falling, your output will also fall or show it as a no change. So that is a concept of positive unnateness. Correct? Guys, are you agreeing with me?
Yes, ma'am. Yes, ma'am. Yes, ma'am.
Yes. Yes, ma'am. Yes, ma'am.
I want someone, my throat is paining, I want someone to explain me for NAND gate. Very simple. If I explain for this, let me see who all are there in life for it.
Hello.
Darshini,
Hello.
Darshini, are you there?
Yes, ma'am.
Sorry, I have a doubt. Hello.
Yeah.
So how can you define a unnateness for a single pin? Because for the previous example, so you took two inputs, right? So 0001, 1011, right? So you have showed only for A being constant like 00, and B you're changing from 0 1. But what if it is a different case? So it will also depend on the other pin, right? So how it will only depend on a single pin?
So I'm not saying that with respect to this, if you look at over here, right, this pin Z with respect to one pin also is positive uniqueness. If you would have done it same for B, right, you can keep B constant and change A.
But
Okay?
what if your B is also changing? Then how would you judge it? Because you're just putting the you're putting the one pin constant and changing the other pin. So that's my question.
I didn't get your question. I mean, see, at the same time, you're stating.
Hello? Yeah, if both are
Ma'am,
changing, then what's the case? How will the unightness be defined?
See,
Then
there
I
is
think there is no uniqueness if both are changing.
Ma'am, he is asking that for not get, madam. A single in.
No.
See, even if you take a buffer, right? See, it's very simple case. For example, if you're taking a buffer, okay, if your buffer, it shows if your input is rising, okay, there is no two pins, okay, I'm keeping one pin. You understood simple that if your input is rising, your output is also rising or no change. Let's eliminate the case of no change. If your input is falling, your output is also going to fall. Okay.
Correct.
Now
Yeah.
in buffer, what does a buffer do?
If
Yeah,
input is
it
rising,
just
then output is
replicates.
also rising.
It just
Whatever is
replicates
the
your
input,
input. Yeah,
whatever,
it will replicate.
if your input is rising, you will always have a rising.
Correct. Yeah.
Have a falling. So that's the simple. The way to explain me for just so that in case of two inputs, buffer it's very simple.
Yeah. For
Buffer is
buffer,
going to be
simple. Yeah.
positive only. Your what you call inverter is going to be definitely a negative only.
Correct.
Okay. Now whom did I choose for NAND gate? I took somebody's name, right? Praveen, you are there?
Yes, ma'am. Can you hear me? Hello?
Yeah, Praveen, you are there, right?
Can you hear?
Yeah. So
Yes,
Praveen, I
ma'am.
need your help to understand me the unightness for a NAND gate. Okay. A, B, y is equals to how do you do a NAND gate? A dot. I have 0, 0, 1, 1. Praveen, what would be the output?
Like for 1 it will be 0, and for rest of all it will be 1.
Okay, sure.
Yes, ma'am.
Okay, great. So now, what will happen now? How will you explain me? Let me. You want guys? Do you want now me to keep B as constant? If, for example, if you guys feel that I am wrong with respect to this, I am also. Let us check now for B. Okay, B is where because the combination doesn't show it good for this, right? Let us keep combination as 0, 0, where B is constant, and 1, 0, 1, 0, output is 1, 1. Let me keep this combination together, 0, 1, and 1, 1, right? Guys, now I just replace the input and made it in this format. You're fine with it, right? So that now I can just club it so that I made it for the ease. Understood, right? This
Yes, ma'am. Yes, ma'am.
combination I clubbed up and keep it together, these two combination, and here. Now I am keeping B constant. Okay, now explain me. The person
If
who was answering.
like in the case of NAND, if one input is 0, then output will be the
In this case,
always
right,
one,
B is
always
constant.
one,
B is
always
constant.
one.
A is making a transition from 0 to 1, right?
Yes, sir.
So
Yes,
what
ma'am.
is my output making any transition?
No,
No, ma'am. No change.
no, ma'am. No
So
change.
this is a combination of no change. Let's say now my B is being stuck to 1.
Yes, ma'am. Then opposite, like
Now my
it's
this is making a
above.
transition from rise to fall, fall to rise, correct? This is
Yes,
falling
ma'am.
transition, correct?
Yes, ma'am.
But what is happening over here? This is a rise transition and this is a fall transition. It's
Yes,
exactly
ma'am.
It's a
happening is opposite, right?
negative uniqueness.
So what happens is when your input is making a rise transition, your output is making either a fall or no change. And when you are making it as a fall transition and your output makes either a rise or a no change, ulta, opposite. It is called as negative uniqueness. Very simple to understand. Okay, all your AND gates, if you take an example, you draw it on yourself and understand. If you take AND gate, OR gate, and your buffer, they will show you positive unnateness. If you NAND, I have drawn as of now, NAND, NOR, and very simple, your what you call it.
Ma'am, I have a question.
Hmm.
So for XOR gate, both are changing. So
Hmm.
can we? So there is no unitness, na?
So now let us draw the XOR gate.
XOR gate.
A 0 0 0 1 1 0 1. Please tell me what's the output and set an XOR gate.
0 1 1 0.
0 1 1 0. Whenever there is a difference in the input, it will produce an output. If both the inputs are same,
Yes,
it will
ma'am.
produce an output. Okay. Now let us continue. What happens is, now guys, I'm keeping A as constant. Okay. Now P is making a transition from 0 to 1.
Yeah. So Y is also making 0 to 1.
Okay, so this is making a fall. This is also making a fall. So this is fall. So I'm also getting a fall. Now take like
Rise, na? 0 to 1 rise.
sorry. A rise. Okay, this is also making a rise transition. This is also making a rise transition. Okay.
Yes, ma'am.
Input is also making a rise transition. My output is also making a rise transition. Now, let's say your A was fixed to 1 1. Now input is
Ah,
making
rise and output is falling.
the rise and falling. Now what there is, can you understand, is there a uniqueness being defined? Because for one case, if your input is rising, your output is rising. But for the other case, when your input is rising, the output is falling. You're not getting a clear-cut picture. It's neither falling into the category of positive unnateness nor into the category of negative unnateness. So they are called as no unnate. If you open up an XOR cell, you will find it over here. There is no unnateness. Okay, so there are broadly the unnateness categories are only three different things. Okay, here no unnateness category because the tool is not able to identify whether should I go from rise to fall, fall to rise. Okay, it's impossible for the tool to determine. So there are only two such cases which is possible only for XOR and XNOR gate. Okay, so
Okay.
there you will have something called as no unnateness. Okay.
Okay.
Hello.
So now you understood for what is the unnateness, and this unnateness is going to be present only for what I said is your combinational cells, right? And this unnateness, you have to also remember, right? In library, it is present in the attribute timing sense. Okay.
Hello.
Hello.
Yeah. So, like, where do you actually use this unnateness? So, why do you need this information actually?
See, the tool needs to completely understand its functionality, right? You and me are getting that AND gate, if my this is rising, my this is rising. The tool is not aware about it. Okay, so how will I function? If my input is changing, should I go rise or should I fall?
Okay.
Because
Got it.
normal human being, right? We have studied it. Okay, we are able to draw it. Tool doesn't know the AND gate functionality or gate functionality. You have to tell the tool. See, I'm telling you positive unnateness, man. You have to make this kind of changes.
Okay. But
Okay.
for the case, right, no unnateness, you just defined, right? So there is no unnateness. So then how do the tool decide for that case? So if you're trying to decide it by unnateness, then for a case like you said that non-unnateness is there, it exists for an XOR gate, then how does the transition being defined for that XOR gate then by the tool?
XOR gate, I need to look at it. See, there is one more thing which is being defined over here within your library. There is a thing which is called as function. Okay. Within all of the cell will also have a functionality defined stating A and B, A or B. So that is also being used by the tool to understand it. Okay, there is a description. But with respect to XOR and XNOR, the tool, I will check upon it that how does the tool understand if no
Sure.
unnated.
Yeah, sure.
I'll check and get back with you.
Sure. Yeah.
Okay.
Yeah.
So this we have looked upon the unnateness and
Hello, ma'am.
hello.
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 Yes, ma'am. That thing I didn't got. You said that in the CMOS, like rising time will be more. That point, why it will be more?
You're asking about that so that graph which I drew, for example, this
Yes,
one,
ma'am.
right?
Yes, ma'am.
This is very simple related to your, I would explain, just go once through your mobility concept. The mobility of your holes versus your mobility of your electrons. You will get to understand this. That it takes higher time for the PMOS to charge up and the NMOS discharges quickly. Okay, that's why when you look at the rise and fall transition, it has to do only with the concept of the mobility. Just I was trying to explain it with respect to your delay value, that always your charging time, right? Because charging is done through in CMOS. Then why it is called as, you guys have gone through the concept of pull up, pull down transistors, right? In your BTech,
Yes, ma'am. Yes, ma'am.
right?
Yes, ma'am.
So, but
Yes,
because
ma'am.
it helps to charge it to the value 1, NMOS is the one that brings it down to the value 0, that helps in, right?
Yes, ma'am.
So the mobility of electrons is higher as compared to you would have used an equation mu n approximately equals to 2 mu p. Okay, this is a semiconductor physics. I'm not going deep into
Yes,
this,
ma'am.
right?
Yes, ma'am. Good.
Okay.
Thank you. Thank you.
Okay, so from this you understood that the combination cells will have these kind of details. Okay. Now let me move down to, okay, the timing arcs related to your flops, right? Whatever you have right now understood related to innateness, that was the timing arcs relationship for your combinational cells. Okay. Now whatever you're studying is thing which is related to your flops, right? So see, everyone would have looked upon the structure of your flops, right? Guys, yesterday when I was explaining you the concept, I explained you that majority of the flops that are there that are being converted to your SDF, which is scannable D flip flop. As of now, I have taken up the example of, see, because in the industry standard you won't look mux as something different and there is a flop sitting. The timing library team itself gives you an SDF which has been available internally of this, right? You know the internal structure of this, how will it look, correct? I gave you an example yesterday. This is a block which is an SDF. It will internally have a mux followed by your this pin. So this will have something as your data pin or data pin, then your scan input pin, then something will come as scan enable, and then you will have Q bar, something which has been available to the outside world. Then you can have your preset or clear logic, something which is CDN over here, right? CDN stands for, when you look at this, it stands for clear data negative. It is something which is activated when it is low, active low input, right? When you say, okay. So this is internally, there is no different mux and this. The standard cell library team will itself give you this block. Okay. So now you would have looked at upon, there are different setup time, hold time, right? So you need to understand the setup time, your fall time, your recovery time, your removal time. All this have relations with respect to what all pin, right? Earlier when we looked at the innateness of Z pin with respect to A pin, the innateness of a Z pin with respect to your P pin. Okay. Now here we are in this diagram we are trying to understand what's the relationship between your different pins. Okay. So what happens is, right, this is a clock pin. Okay. This is also an input pin. This is your Q pin, which is an output pin. Okay. So now what happens is the relationship always between an input and the output is always terms it with respect to delay, right? Now what happens even in your combinational cells, okay, cell rise delay, cell fall delay, it all depends upon your, how was your input transition pin and what was your load, right? So whenever there is a relation between input and output, it represents the cell delay. It can happen for the cell delay, how the transition is made, whether your input is a rise transition or input is a fall transition. Okay. This major concept of setup time and hold time is for how does your data and your clock correlates with each other. Okay, that is something which is between two input pins. Okay, so then you have a concept of setup time and your hold time, and similar goes. See, when I'm saying setup hold time, you consider whether it is making a rise transition, fall transition. There are these two possible cases. Okay, and there is something which is also in depth. We'll learn it later. The relation between the clock and this your CDN pin. Okay, clear data negative. You call it as normally you can call it as clear pin or reset pin. Okay, so how, if this is all related to how you have to deassert or assert a logic, right? This is an asynchronous thing. All the rest which we are looking at it have a synchronous relation, but this is asynchronous. This is a complete different concept when you are studying ST. I will explain what a recovery removal is. It's also, recovery is very similar to setup. Okay, removal is very similar to hold. But instead of with D, it is now with an asynchronous pin, which is called as clear. Okay, so now this information to us, we have explained it in this time of diagram. Okay, now the tool has to explain it in terms of library. Okay, so how will the tool explain it in the term of your this, right? So this has been explained in this slide. Okay, now let us say, for example, you understood pin D. Okay, your flock pins. Okay, now this is related to clock pin, right? Every time I'm stating you, right, you will have something as related pin. When you will open up your reset or recovery or removal, you will have, instead of D, you will have CDN or SDN. There are different naming convention used by different. So you can correlate, okay, now this arc between D to clock is either going to be a setup or it is going to be a hold. These are the only two possibilities between these two pins with D and CK. Okay, so one is either setup, one is hold. Okay, so as I stated, there can be rise related details, fall. See guys, I cannot put all the things over here, just for a frame of understanding. I have mentioned it over here. Now a lot of times when I look at the folks, right, they have a very wrong perception that whatever the setup time and hold time is there, right, it is not a hard coded value. Even the setup time and the hold time is a kind of a lookup table. Okay, it is a lookup table between, see, I took specifically this example to understand you. It's a 2D lookup table between your data transition and your clock transitions. Okay, so first is index 1 is trying to say that how is your input D pin making a transition and how your input pin clock is making a transition. Depending upon these two transition, I will come up with the values of setup and hold. Okay, you just, if you have something with if you have the tool, just try to do is what you make your transition go bad on your data pin. Okay, and the same timing corner and everything, you do this analysis, try to make your transition bad. Okay, and then when you dump a report, timing report at the your, you will look at your setup time. Okay, when you look at the setup time of the one which was with a good transition time, you will find a lesser value. The one which you look with, you made a bad transition, you will look a very higher value. Okay, so understand this setup and hold time is never a hard coded value. There is no specific value. Okay, this block will have this much setup time, this one hold time. Okay, so this values for this timing are related between D and CK pin is explained also in your library. So that tool, when it does its timing calculations to find out what is the setup time, it will come over here, look into the section. Now this is for related to hold. You will also have with related to setup. Okay. So now, for example, this one I put it with the setup, right? Okay. So this is with respect to the setup, right? So you understood from this, like how will be the timing related information. Similar will be there for recovery, removal. Okay, guys. Just here the pin name would change as your CDN. Instead of hold rising, there will be a recovery rising. There will be a recovery falling. There will be a removal rising. There will be a removal falling, because it has to do for all the various possible combinations. If my input is making a rise transition, then I have to do that. So this is all being done by your library characterization team. They just give you just have to utilize it, but you should know aware about it. See, very hardly the people in the industry open up this to look at it, right? Because all the majority the tool does, when it does the dumping, we are very much sure that the tool would have done it in the proper way. But you need to understand from where does the tool took this value. Okay, when the tool is giving you, and yesterday I stated you that output of your this synthesis process will have a lot of reports, timing report, power report, area report. So now how will the tool come to know the area? It will calculate, okay, I have 5 AND cells. The AND cells are of different drive strength. Okay, this is a calculation. I will go into the library, combine all the area of this 5 AND cells. I have 10 OR cells, so it will do this, right? So this is the way. It is not some rocket science. It will just go into the library, calculate it, cumulative, it will try to dump the results. Okay, this is the final area report of my design. Okay, so this is something about, I tried to complete it about your timing
Ma'am,
level.
excuse me, ma'am.
Huh?
So previously for the combinational cells, when you are explaining this cell delay, I mean propagation delay. So here also, if you are mentioning about PIND and you had mentioned for hold rising, so the values are like this. I mean for hold values are like this. So when we are mentioning hold falling, then also the same case which you have mentioned in the combinational case, falling it will be lower delay, right? When compared to the rising, the delays. So the same scenario, the same kind of analysis will hold true for this deep-in also. I mean, for whenever you're checking hold falling, the delay values are lesser than the hold rising values. Is that hold true for here also?
See, there is a very different concept, even that the hold time. See, you don't know how the internally the flop is being made, right? If you would have looked, there is a way now, right now, the whatever library I have it, right? You look, all the values are positive. There is a very different vast topic that I wanted to cover it later, that even these values can be negative, you know. You don't have to be very much shocked that how can these values be negative. See what happens when the standard cell team would have designed this libraries, right? They would have made like internally you feel that okay, every time the this flop is going to be, for example, right? Let's see, now I'm not drawing this one. You internally will feel okay, this is my D pin, this is my clock pin, and this. Okay, but internally the structure can happen that when your flop is there, right, the pin you look at D, it can go through lot of buffers inverter combination and then it is reaching your D pin. Okay, that is a complete different concept. I'll try to explain in any different lecture that why this whole time is negative, but this doesn't hold true that every time your values will be in proportion with respect to that. Rising will have a lower value while your this falling will have a value, because in this internal structure we are not sure, right? With respect to standard cells, we know that standard cells will not have any internal structure with respect to standard cells, right? It is just combination of uh, the CMOS, correct? But this, we can't state it very sure true that this is going to hold true over here. If you would have looked into a library, or you can just Google it, I'll explain you in a different lecture, because this lecture is intended for this cell. Why this the library whole time and this can be negative. Okay, so
Okay,
this
ma'am.
is over 2 years.
Okay, ma'am.
So this is all about your which library which I talked upon till now.
Timing library.
You call it as timing library, but I just termed it as timing library. Don't call it as timing library. Call it as
Logical
logical.
library.
Because see, main intention primarily is to have timing information, but it also has power related information. It also has your area related information. So these are all the logical attributes, right, of your cell, correct? Guys, are you
Yes,
Yes,
up
ma'am.
with
ma'am.
me? Okay. Just a moment, okay, just a moment. Let me know once my screen is up. Is my screen visible?
Yes, ma'am.
What? I'm not sure what's what is on my screen?
That pin D setup and hold rising.
Just give me a moment. Just give me a moment. Just let me know once my screen is up.
Yes, ma'am. PPT is showing timing library contents.
Okay. So This is something like I would like to conclude and try to explain you what completely you understood about the timing library. Okay. But now, can one person answer what are all the contents of timing library? We looked at it. Anyone, at least. Okay, let me go ahead. Manish, are you available? Guys, I'm speaking from past 2 hours. At least say yes.
Yes, ma'am.
You're available? Okay. So, just tell me any one content out of this complete 2 hour session you understood that is present in the timing library.
Yeah, in timing library, we can see the input transition and the rise and fall time, and
Rising input transitions, whether it's rising, falling, how is it useful to you? How does it help you? It helps you to calculate what. See, you're not in your main intention is not to look at what's the rise and fall transition or what's the load capacity. The main intention behind it is to calculate.
calculate the timing, if does it meeting or not.
Yeah, so it helps you see transition is important, but this transition information we got it from slew, right? The slew information that how much the tool calculates gives 30% to 70%, 20 to 80%. But at the end, you were calculating the delay. Okay.
Yeah.
Fine. Then Hari, what we learned? Anything else within this library?
In about logical and physical library.
Hari is speaking.
Yeah, logical library and physical library.
Okay. Logical library. What the content you understood? Logical library. Within logical library, what did you understood?
Like within the logical library, we can see the parameters of
And transition. Say something
yeah,
else.
parameters like area, pin directions,
Okay.
input
Area.
and
Fine.
setup and hold time.
Okay, fine. So guys, at the end, you understood that it has all the logical parameters which is related to your PPA, whether your timing, your area, your power, correct? So
Yeah.
just to wind it up, I'll just give you a summary that you first looked at the cell definitions, right? What are the different kinds of like cells which are there, right? At the start, it was mentioning cell and gate, cell, whether it's an on gate or it's a D flip flop, right? So it has the cell definitions. Within that, each cell you have something, subsections of pin information, right? What are the pins? Whether the pin is input pin, whether the pin is output pin, correct? Then you looked at something as timing arcs, like how timing arcs related means how is the unnateness related thing, whether it's a timing sense or timing type, whether it's a combinational, sequentials, you understood that. You even it has the capacitance value. See, that's also big. If you open up the timing, once we are doing this lab sessions, I'll give you one to one. There are capacitance value as well, right? For each of the cell. Okay. Then there is something which is related to your flops. You have setup and hold time related. Setup and hold is a very broader category. Recovery, removal, all the timing arcs related to your flops are there. Then you have all the power related information which I showcased you for leakage, right? How all the combinations affect this power information. Then you have delay and your transition tables. At the start, you had your PVT units being defined. Okay. So in today's lecture, you understand in depth about how does a timing library and overall view it looks like. So the contents of the timing library is very huge. I cannot put the library itself over here. But just to framework to explain that you should be in answerable position. Like for example, how does the tool calculates the area? You should know that okay, it calculates how many what are the quantity of cells in my design. What is I will go into the library, try to make a cumulative of it. If somebody asks you how does the tool calculates the delay, why are you giving the input as library, right? Until and unless you have this library file, your tool is unable to calculate the cell delay. Okay, so overall framework you understood from this lecture that what are the contents of the timing library, or you call it as logical library. Okay.
Yes.
So we'll continue the next lecture. Maybe I'll update
Ma'am,
you.
actually, you have mentioned at the last we can assemble some doubts, right?
Yeah, actually, this next session got a bit delayed. I have to step out. I have a doctor's appointment around at 8.
Okay, ma'am. Okay.
But maybe like tomorrow I'll set up, like we can have the initial 15 minutes for the meeting, or better, you just jot down the question on this. You have a WhatsApp group, right? Just
Yes,
jot
ma'am.
down the question and list down over there.
Okay, but you are also in the group?
Yeah, I'm also in the group.
Okay.
Okay, because today
Ma'am,
lecture is postponed, so that's why I already have a doctor's appointment booked that day.
ma'am, just one question, ma'am.
Yeah.
Ma'am, that you told now that PVT kernel also for suppose AND cell for different PVT kernel will have different characteristics. So all the characteristics are written in a same library file, or we have different
No.
library file.
See, then the library file will become very bulky, correct? See,
Okay,
in the
okay.
same library file itself, you have a 15-20 lakhs of such attributes, right? Every MCMM, every different PVT corners will have a different this one. When you look at
Like
your thing, right, you will have the dot lib will have something as TSMC5 standard cell at this process, this FFG 0C 125 degree. Then you will have a different library file, so that you don't have to internally see if you are doing an analysis in one corner. Why will you open up the file which has all these things? You will directly open up that file in which you are doing the analysis, right? You're doing at SSG corner at this temperature. So they don't want to make it bulky. And this is very easy bifurcation, right? So, okay, this complete file has all the cells being characterized at this PVT mode. So that is why when you take it as an input, it is not single library. It is different library across all PVT corners.
okay, ma'am.
Okay.
Okay, thank you, ma'am.
And
Yeah.
the group you have mentioned is PD group main group, right? PD main.
Just give me a moment.
PD main premium job, I think.
Sorry.
There is a group VLSI for all PD main.
PD main.
Today we got an information that we'll have the class at 5:30. PD main.
Okay, ma'am. Thank you.